All right, welcome back everybody. Today I am going to do a quick video showing how to solve the participation activity for Econ 100B Intermediate Micro. So what we're going to be doing today is a little combination problem looking at firms and production and costs. And this is all breaking down production functions and how firms behave in the short run and the long run, looking at how firms decide how much to produce. And so the first problem is looking at a sort of modified production function problem. So the problem says, basically looks at how two different students can produce a grade given on how many hours they give to solving two kinds of problems. So we have Will, who can produce a higher grade on his econ exam by spending a certain number of hours on either analysis problems or supply and demand problems. And so given by the problem or by the assignment is Will's production function for a given grade. And so that's going to be, let me pull up this. There we go. That's going to be Will's grade is a function of, it's a production function with a constant 2.5, and then A is the number of hours spent on analysis problems, and R is the number of time spent on supply and demand problems. And right away we can notice that Will's production function for his grade is a Cobb-Douglas production function. We're going to deal a lot with Cobb-Douglas production functions because they're very common and they give us a lot of really great intuitions that we can use. So Will's roommate, Dima, has her own production function. Her production function for her grade is the same basic format, but she's got a different technology. So Dima's production function is 2.5, and then a function of hours spent reading analysis problems and hours spent doing supply and demand problems. Also a Cobb-Douglas production function. So we want to find the marginal product of studying supply and demand problems for Will. So Will's marginal product of R. And then we want to find Dima's marginal product of R, those supply and demand problems. And then we want to find Will's marginal rate of technical substitution between studying the two types of problems. And remember that marginal rate of technical substitution is the ratio of the marginal product of our two inputs. So normally we're looking at labor and capital. In this case, we're looking at analysis problems and supply and demand problems. And it's also going to be the slope of the isoquant curve for a certain level of production. And that's going to become really important in Chapter 7 when we compare them to isocost curves. So that's going to be really, really useful. And it's also parallel to what we looked at with consumer choice, right? The indifference curves had the marginal rate of substitution, which was the trade-offs between two goods of consumption. Now we're looking at the trade-off of two different types of goods, of two different inputs. Cool. Hopefully that makes sense. Sorry, I got a little sideways there. So let's go ahead and solve this problem. So first we want to get the marginal product of supply and demand problems for Will. In order to find Will's marginal product of R, we want to remember that, and this is, if you want a more detailed explanation of this, you can go to the appendix. Explicitly in the book, we don't use a lot of calculus. We use an algebraic approach, but a lot of it is derived from the calculus approach, and so you can go in there and look at the appendix if you're interested in it. Basically, the way we derive the marginal product of a given input is to take the partial derivative of the production function with respect to that input, which if we have our production function is Q equals A, L lowercase a, K lowercase b, then the partial derivative is A, taking that exponent down here, L, A minus 1 KB. This is unchanged because we're only taking the derivative with respect to L, and that just means that we take this exponent down, put it up here, and subtract 1. When we solve that out, what we get for that marginal product of labor is that we can set the marginal product of labor equal to A times ALA-KB divided by L, which this is our production function. So we can turn that into AQ divided by L. And that's a pretty easy formula, right? So for our Cobb-Douglas production functions, the marginal product of a given good, or a given input rather, is that exponent times Q divided by the quantity of labor we're using. So in this case, looking for Will's marginal product of supply and demand problems, what we can do is insert those numbers into this here equation. So set Will's marginal product of these problems, right, of marginal product of R is going to be equal to that exponent B times Q divided by R, or in this case, because we're talking about kind of different things, we're going to say the marginal product, of those supply and demand problems, R, is equal to 0.64 times GW, the grade he wants, and the number of problems he does. So that's that marginal product. And that gives us a marginal product for of those problems for Will. We do the same thing to find the marginal product for Dima. Dima's marginal product with respect to those supply and demand problems is going to be 0.75 GD divided by R. And so those are the marginal product of studying supply and demand problems for Will and for Dima. Make sense? Yeah, that's not a very good D. Let's try that way. To find Will's technical rate of substitution, we need to find his marginal product of supply and demand problems and his marginal product of analysis problems. So I'm going to get rid of Dima's stuff now and just focus on Will and get that marginal rate of technical substitution. So, thank you, Dima. So we have marginal product of R is equal to 0.64 GWR. The marginal product of analysis problems is going to be equal to 0.36 GWA. And then we want to remember that the marginal rate of technical substitution is the slope of that isoquant curve. The other way we can think about it is we can say that the marginal rate of technical substitution is equal to the ratio of the marginal product of our two inputs. So we have, if it was the marginal product of labor and the marginal product of capital, it'd be the ratio, the inverse ratio of those. For our purposes, it's going to be the marginal product of A divided by the marginal product of R, which is also equal to, if we are holding the output constant, we can say it's A Q divided by L over B Q divided by K, or in this case, A and R. And basically what we're doing is with these Cobb-Douglas production functions, I feel like I don't want to lose you guys here. There's a format for solving all of these that just uses our different constants, right? That overall form of sum Q equal to sum A, sum L, some exponent for L, some level of capital, and some exponent for that capital. And so there's, in the book, in the solved problems, in the appendices, and in the homework assignments too, there are all these different tricks and techniques for solving these that have proofs that have already been generated. And so I'm not saying that you don't have to think about them, but what I'm saying is we can make use of the shortcuts of knowing that there is a set formula in place here. Does that make sense? So we know what the marginal rate of technical substitution would be for this formula. It would be inverse of marginal product of labor to marginal product of capital, which is equal to AQ divided by L over BQ divided by K, which is equal to negative A over B times K over L. So what we can do is we can use this same formula because we know what our exponents are, and then just insert K and L. So for finding Will's marginal rate of technical substitution, we can come in and say, okay, the marginal rate of technical substitution for Will is equal to the ratio of those exponents, negative 0.36 divided by 0.64 times R over A, which simplifies down to 0.5652 RA. Don't forget the negative sign, or it will be wrong. Sound good? Kind of makes sense? We could do the same thing really easily for DEMA if we wanted to. It's just going to be DEMA's exponents. So 0.25 divided by 0.7 times RA would give us negative 0.35 times RA. Sound good? So again, try to think about these problems as being solvable in these ways where there is a system in place, right? There is a method to the madness, a sort of a formula that we can all use. So that problem comes from chapter 6. This problem comes from chapter 7. I believe it's also a problem in, I know the will and the studying problem is a problem in the homework. I don't know if this one is, but I think it's useful because it touches on a couple of things that come out of chapter 7 and are really useful in terms of reminding ourselves about what the implications are of everything we've learned so far. So number 2 says, a U.S. company is deciding whether or not to move production abroad. And so we have a lot of information built in here. It's going to be another Cobb-Douglas production function. So the company has a production function, Q equals L 0.7, K 0.3. And this is a long run production function. So we want to think about both the wage and the rent and the reality that we can change both labor and capital. So we have a wage equal to 7 and rent of capital is equal to 3. And then it's given by the problem, but it's also something we just found, right? If I wanted to find that marginal product of labor, it's going to be 0.7 Q divided by L. And the marginal product of capital is 0.3 Q divided by K, right? We figured that out last time, and that's a standard thing for our Cobb-Douglas production functions. The last piece of information is that the wages in another country, Azerbaijan, where they're thinking of moving, are 10% lower, and the rents are 10% higher. So if we look at the Azari wages, it's going to be 7 times 1.1, 1.1% higher. That's not right. 1.1% lower. So we're going to divide it by 7 divided by 1.1. And the rents are going to be 1% higher. So that's 3 times 1.1. And that'll come into play in a little bit. So there's a lot of things we want to think about. One of the questions that we can think about is, will the level of, or the level of capital and labor used in production change if we move production? And this gets at something that we didn't talk, it's in the second half of chapter 7, which is this tangency rule, which is basically when we get to talking about isoquants and isocosts, this idea that our isoquant, where we can produce some Q with some combination of capital and labor, is going to be tangent, that didn't work, tangent to some isocost curve. And so the isocost curve has a slope of negative wage R, and the isoquant curve has a slope of negative marginal product of labor divided by marginal product of capital. And so that tangency rule says we're going to produce where marginal product of labor, marginal product of capital, that marginal rate of technical substitution is equal to the slope of the isocost curve. So that's where we're going, and that's what we're going to use to solve this problem. Okay, so let's get this out of the way and start answering the actual questions in the problem. The first thing it asks is, what are the levels of labor and capital? What is the labor capital ratio? To find the ideal ratio of labor and capital, the optimal labor capital ratio, what we want to do is use the marginal rate of technical substitution to solve for the optimal ratio. And you can see this in solved problem 7.3 in the book. To get that ideal labor capital ratio, what you do is you look at the tangency rule, right? Which says the marginal rate of technical substitution should be equal to that, which we know that that marginal rate of technical substitution can also be written as marginal product of labor divided by, marginal product of capital, or negative alpha over beta times K over L. And that's what we're going to use. We're going to, since we want to know how much capital we want to use, we want to set this equal to this and solve for K. So we are setting the slope of the isocost curve equal to the slope of the isoquant curve to find the optimal labor capital ratio given our costs and our technology. So what do we have here? We've got, given by the problem, that we're going to be producing, does it say in the problem? It does say in the problem. We're going to produce 100 units. So Q is going to equal 100. So we can now fill in our formula with our exponents, 0.7 divided by 0.3. And then we have capital times labor. And then we have the wage and rent. And now we solve to try and get to capital, right? To try and get to how much capital we use relative to how much labor we use. So we take this ratio of exponents and pop it over on the other side, which gives us negative 7 times 0.3 over 3 times 0.7, and then multiply both sides by L, gives us K equals 7 times 0.3 divided by 3 times 0.7 times L. Turns out that's 1L. So our optimal capital labor ratio is 1:1. So we want to use equal parts labor and capital to get to our quantity of 100. Our ideal capital labor ratio is K equals L. Sound good? If you're a little bit uncomfortable with this problem, go back and look at solved problems 7.3 in the chapter, and they go through, and first of all, they derive the formula where they take it step by step, going from, negative A over B times K over L equal to negative W over R, and then solve it out. And then they get a different result. They get 2 parts capital, 1 part labor ratio, I think. And so it's a nice practice if you're still having a problem with it. So you end up still with that same formula of negative wage times the exponent for capital and rent times the exponent for labor times labor. So now that we have that, we know that our optimal labor capital ratio would be is 1:1. So if we want to insert those into our production function, we're going to see that our level of capital is going to be equal to 100, and our level of labor is going to be equal to 100, and that'll get us to our total desired quantity of 100. If the country moves abroad, the technology of this production function doesn't change. I know that's a little bit weird. We think our intuition is, well, if the prices of them change, that should change the production function. But again, if you think about it in terms of the production function being given by an isoquant curve, and the cost associated with production being given by that iso cost curve, changing the price of labor and capital is not going to change this isoquant or its slope. It's just going to change how much it costs to produce that same level of capital. And that's what we're going to do, is hold that quantity. In part C, we want to hold that quantity of 100 constant and find out how much how much it would cost to produce in each country. So now that we know what our optimal production function is, we know our optimal capital labor ratio is 1. We've got our marginal product of labor, marginal product of capital, wages in the U.S., wages in and rents in the U.S., wages and rents in Azerbaijan, and we want to produce a quantity of 100. We just need to find the cost. And remember, the cost is just equal to wage times labor plus rents times capital. So this is easy, right? So the U.S. cost of production is going to be 7 times 100 plus 3 times 100, or $1,000. The cost of producing in Azerbaijan is going to be 7 times 1.1 times 100 plus, 7 divided by 1.1 times 100, and 3 times 1.1 times 100, which is about $966.36. Does that make sense? Can you see that with the low-key glare we're working with today? Hopefully. So that is how you solve that participation problem. Hopefully that gives you a sense of how to solve other problems, right? We've got a lot of elements here, but some of it's really similar to what we did with consumer choice. And really all we're doing is solving for these points of tangency, solving for costs, solving for marginal productivity. And so these are all relationships that are denoted in the book, and that we can just solve through, right? We have formulas for these based on this Cobb-Douglas production function. So hopefully that helps out a little bit. Let me know what questions you have, and I'll see you all next time.